All right, so like I said, the state, if the caffeine deprivation has no effect on the depression, then we would expect the actual mean difference in depression scores to be 0. And we want to test this hypothesis. And we think that there is a difference, right? So placebo minus the caffeine. So if that's the case, then their depression is going to be greater with the placebo, in the caffeine helps them. So that's the case. This number would be higher than this one. So when I subtract them, I would expect that the difference to be higher than 0. So that's how I get the null or the alternative. You have to think about what we wanted to happen or what we thought would happen. So it says where mean difference equals the true mean difference between placebo minus caffeine in depression scores. Since no significance level is given, we'll use alpha equal to 0.05. So you have to think about what was it. They think that caffeine has an effect and lowers their depression, where not having the caffeine would increase their depression. So that means that this number would be higher. When I subtract them, I should get a positive number, which would mean that the direction of my alternative should be that the difference is greater. So you have to think about how you're going to set up the null and the alternative according to what you read in the problem. All right, so here we go. Plan. So it's random. It came from a completely randomized design. Normal. We don't know whether the actual distribution of the differences in the scores is normal. With such a small sample size, we need to see if it's safe to use T procedures. So again, we look at the graph of what's going on here, and when we do, we find. All right, so if you were to put the data of just the difference column into your calculator, this is what you would see. There's no real outliers. A little bit of skewness here in the box plot, the normality plot here. It's, pretty decent. The histogram is an irregular shape with a few values. The box plot shows some right skewness but no outliers, and the normal probability looks fairly linear. With no outliers or strong skewness, again, T would be okay, as long as there's, pretty much no outliers or real strong skewness, which we don't have. Independent, we aren't sampling, so it isn't necessary to check the 10% condition. We will assume that the changes in depression scores from individuals are independent. So we don't have to, because we're not sampling with replacement, we're actually dealing with individuals, and we're going to say one person's depression score isn't dependent on somebody else's. So we're good to go on our conditions. So they take the mean difference, the data, and then the standard deviation, and again, you calculate the test statistic. Notice that the null is always going to be 0 here, because I told you every time we do a difference, right, the null is set equal to 0. So it's kind of like you don't even have that on there, and you get your T statistic. And then your p-value according to technology, the area to the right of T is 3.53, with 10 degrees freedom is 0.0027. You can run the whole thing in your calculator again by just inserting into a list and spreadsheet the difference column, right? And so that would be it, and then you can check your data and you can run the test. Remember that it's just going to be a one sample t-test. Even though we technically have two samples, it's paired, and after we subtract them, we're down to just one sample data to run our test on, and so it's not a two-tailed. So remember that it's not two samples. So remember that it's not two, it's just one when I have paired data. So again, you make the conclusion our p-value is far less than our alpha, so we have convincing evidence that there is a difference. And then we can say, therefore, conclude that depriving these caffeine-dependent subjects of caffeine causes an average increase in depression scores, right? Because we said that it would be positive, which it is, and so forth. So we know that not to take away their caffeine, they'll get cranky. Again, remember to use your T procedures wisely. Significance tests are widely used in reporting results of research in many fields. New drugs require significance evidence of effectiveness and safety. Courts ask about statistical significance in hearing discrimination cases. Marketers want to know whether their new ad campaign significantly outperforms the old one. Medical researchers want to know whether their therapy performs significantly better. In all these uses, statistical significance is valued because it points to the effect that is unlikely to occur just by chance alone, which means if it didn't occur by chance alone, there's not a very high chance it could have just happened. It means that something caused it to happen, and we conclude that whatever we implemented into the study is what caused it. Carrying out a significance test is often quite simple, especially if you use a calculator or computer. Remember, I showed you can run it all in the calculator from beginning to end. Using tests wisely is not so simple. Here are some points to keep in mind when interpreting your significance test. The null hypothesis of no effect or no difference can be rejected at the usual levels, but good evidence of a difference, when there's good evidence of a difference. But too many differences may be very small. When large samples are available, even tiny deviations from the null hypothesis won't be significant. All right, so just remember that what happens is that if we do have a difference in our testing, if we have a small sample, it's going to look like a bigger deal to us than if we had a big sample. But the converse of that's true as well, that some type of difference won't show up sometimes, depending on the size of our study, and so it becomes this complication in actually analyzing the data and seeing things. So here it says, don't ignore lack of significance. There is a tendency to infer that there is no difference whenever a p-value fails to attain the usual 5% standard. In some areas of research, small differences that are detectable only with large samples can be of great practical significance. When planning a study, verify the test you plan to use has high probability or power of detecting difference of the size you hope to find. So you want to make sure that you have a high power. So something can be statistically significant and have no practical bearing, and something can be practically significant but not be found statistically significant. Statistical inferences is not valid for all sets of data. Badly designed surveys or experiments often produce invalid results. Formal statistical inference cannot correct basic flaws in the design. Each test is valid only in certain circumstances, when properly produced data being particularly important. Beware of multiple analysis. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what the difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. And that's all, finally.